recording. Ready to go? Okay, so welcome everybody to the March FPGA seminar, and this month we have a visitor from UBC. So we have Azam Basol, who's a PhD student with Steve Wilton, working on low power FPGA architecture.
Thanks, Paul. Okay. Thanks for having me here, and thanks for coming to this talk. This talk is done as part of my PhD thesis at UBC under the supervision of Professor Steve Wilton. So I will start this talk by explaining how it fits to the whole thing. So here I'm showing a system on chip. You know, a system on chip is composed usually of a microprocessor and a collection of IB cores, as can be seen in this figure here. So what might be happening at runtime is that some of the IB cores might go into idle state. And during the idle state, they basically consume static power or leakage power. And this is bad because we are wasting power and we are not doing anything. So for example, if IB core 2 goes into idle state, the best thing to do here is to turn it off using a circuit technique that's called power gating. So we want an architecture to support that. So this is done dynamically at runtime. If IB core goes on again, it works. It has something to do to execute. And IB core 3 goes into idle state. What we want to do is to turn on IB core 2 again and turn off this new idle IB core to save the power consumption. And we want to do this dynamically at runtime. So what this talk is about, we want to support this in FPGAs. We want an FPGA architecture that can support this feature in order to reduce the power consumption of FPGAs. So, as I said, we want an FPGA architecture that supports dynamically turning things on and off at runtime in order to save the power for idle components. And this figure here shows basically the idea. If we have an FPGA, and we have an application that has two subcomponents, for example, island 1 and island 2. When one of these components go into idle mode, we want to turn it off to save the leakage power of that component. And this is done using some on-chip control. This control could be synthesized on the on-chip resources of the FPGA. And these control signals that come from this controller are routed using the FPGA resources. ASIC designers do this regularly in their designs to reduce the power consumption of their chips. In FPGAs, however, there are some challenges that are not faced by the ASIC designers. Some of these challenges is that we don't know about the application when we design the architecture for the FPGA. Also, how to route the signals using the routing resources if some of these routing resources could go into idle state and could be turned off. Another challenge in power gating architectures in general is the handling of wake-up current. When we wake up the components, there's a large current, and it has some consequences. So how we could handle this wake-up current? So I will go in this talk and talk about these challenges. But before that, I will talk about the motivation for this kind of architecture. So we know that FPGAs leakage is becoming more and more important as we scale the technology. And in recent technologies, as shown in some white papers from Xerox and Altera, static power is becoming the same amount as dynamic power, which is interesting here because dynamic power is not the major component of power consumption anymore. It is becoming static power and dynamic power both the major components. In high-end FPGAs, we can see that each year FPGAs becoming more dense, meaning that they have more cells inside them, millions of cells inside them. And we are approaching a point where maybe we cannot turn on the whole FPGA at the same time. So in order to have these FPGAs around, we want a technique that can allow us to turn things off in order to limit the amount of power that's consumed by these FPGAs. And in mobile handheld devices, the reason is obvious for this kind of architecture. We want to reduce the power consumption in these devices in order to prolong the battery life. And many of these devices, they have many idle viewers in their regions, and they could take advantage of this architecture. In fact, if we have this capability in FPGAs where we can reduce the power consumption, whether using this technique or other circuit techniques, we can have FPGAs more commonly used in these applications, which may result in a boom in the FPGA industry. So this is basically what are the reasons for this kind of architecture. And I would like to talk about some relevant work that talks about saving static power in FPGAs. So here I'm going to talk about what we call statically controlled power gating. But before that, let me explain to you the idea of power gating here. So here I'm showing a logic cluster or whatever circuit component is this. And instead of connecting the power lines of the logic cluster directly to the power supply, we are connecting it through a PMOS transistor. So this PMOS transistor is called a power switch or sleep transistor. Basically, if we turn on this sleep transistor or power switch, the logic cluster will be turned on, meaning that it will function as usual. If we turn off the sleep transistor, the logic cluster will be in the sleep mode, and it will consume small leakage because the leakage will be limited by the leakage of this PMOS transistor. And there are some area and performance trade-offs here because the size of this PMOS sleep transistor determines how much area overhead you have, what is the performance degradation because of the voltage drop through this PMOS transistor, and so on. What I mean by statically controlled is that using this S1 configuration bit, you can configure this PMOS transistor at configuration time, whether the logic cluster will be in sleep mode for low power or in active mode, which basically consumes power. And this can be done only for unused resources in the FPGA. The limitation here is obvious, is that we cannot really turn things off at runtime when they are idle. So basically, this applies only for unused resources. Some other works in the literature propose using dynamic reconfiguration to basically reconfigure the resources at runtime to be in the sleep mode during their idle periods. However, there are some challenges. For example, dynamic reconfiguration can be done at very coarse granularity. There's some power overhead during the reconfiguration process, and there's no really architectural details of how this can be done during dynamic reconfiguration. Also, other works, as shown in this figure, propose using one sleep signal to control part of the chip. So if we assume that these are regions in the FPGA chip, and they can basically sit to be in the on mode, off mode, or controlled by the sleep signal. And the disadvantage of this is that basically you can create one power domain. You cannot create more than power domain. So you can create one power domain that is controlled by this sleep signal. So this is a limitation. Our architecture, or the architecture that we would like to have, is an architecture that allows us to create as many as we need power domains. In commercial FPGAs, there have been some technologies. For example, in Altera's FPGAs, there's a programmable power technology, which basically allows the tools to configure the amount of threshold voltage for logic blocks on the critical path and off the critical path. So basically, decreasing the threshold voltage for components on the critical path to increase their performance, but they become more leaky. And off the critical path, the components have larger threshold voltage, and they become less leaky. But this is done only at configuration time. It is not done at runtime. For embedded blocks in commercial FPGAs, unused embedded blocks like memories, DSPs, PLLs, transceivers, they are turned off at configuration time. There's no runtime control for these components. In micro-semi FPGAs, there's what's called a flash freeze mode, which is basically a low power mode that puts the whole chip in low power, and it returns the values stored there. But this is done for the whole chip. It doesn't allow controlling regions inside the FPGA. So what we really need, and what we propose here, is an architecture where we can control the power state of the regions in the FPGA based on their behavior dynamically at runtime. So this is what this talk is about, and this is what we propose in this work. So this is my outline for this work, for this talk, for the next slides. I will start talking about the architecture details for the power gating architecture that I'm proposing. So this shows the big picture for the architecture. Here is an FPGA with regions. So basically we divide the FPGA into regions. Each of these regions could be controlled in terms of power at runtime. And the control signal could come from on-chip, maybe from a power controller that's synthesized on the FPGA resources. And the control signals are routed, as shown here, using this blue and red control signals, are routed on the routing resources of the FPGA. So basically, we don't want to change the routing architecture for the FPGA, so that we can route these control signals to these regions as if we would like to route any other signal. So I'm going to talk about some of the architecture details related to this architecture. So here I'm assuming a region with a granularity of one logic tile. As can be seen here, this is a logic cluster surrounded by the routing resources, switch boxes, and routing channels. These routing channels contain track isolation buffers and connection blocks. And in our architecture currently, we are doing power gating for the logic clusters and the surrounding routing channels. We don't do power gating for switch blocks right now. And here I'm showing a zoom in of the power gating circuit for a logic cluster. So basically we use this sleep transistor that's driven by the output of this 3-to-1 multiplexer. So based on the configuration bits that determines the select lines for this multiplexer, the sleep transistor might be in the on state or in the off state, or it could be controlled using this signal, which is the control signal for the power state. So this signal comes from the routing with FPGA, and I will show you how this signal could be routed on the FPGA routing resources later. So this is basically the basic power gating circuit for our logic cluster. Here I'm showing two logic clusters side by side, and the purpose is just to show you how we are doing power gating for these routing channels. So if you can see here, this routing channel is shared between these two logic clusters. And basically the routing channel is a set of track isolation buffers and the connection blocks here. So these track isolation buffers usually are shared between the two neighboring logic clusters. And when we turn off these routing channels, we have to make sure that both of these logic clusters are turned off. So if any of these logic clusters is not turned off, we must maintain this routing channel on so that it will provide routing for the on logic cluster. So to do this, basically we use this AND gate, and we use it to AND the control signals for both logic clusters, so that the result of this ANDing is the control signal for this routing channel. And as I said before, currently we are not doing power gating for switch blocks, and it is our focus for the current work. Now, how these control signals are routed on the FPGA routing resources. So basically they could be routed as any other signal could be routed. But to connect them to the BMOS transistors, the sleep transistors, basically what we do, we take one of these inputs to the logic cluster, one of the bordering inputs to the logic cluster, and we select one of them using a multiplexer here. So the selection for this multiplexer is done at configuration time, using these two SRAM bits. So in this way, we can have any of these input pins, or maybe subset of them, to be fed to this multiplexer, and one of them could work as a power gating signal. So basically, you can route this signal from anywhere of the chip to these input pins, and you can use it as a control signal for your power state. We know that input pins are expensive, but we argue that some of these input pins might be unused for some of the resources, and we can use them for this purpose. So, to reduce the area overhead that results from power gating from the sleep transistor and from the extra multiplexers, we can do power gating for a region of the FPGA instead of doing it for one logic cluster. And this is interesting because there's a trade-off between the size of the region and the area overhead. Also, there's a trade-off between the size and the CAD difficulty, and I will talk about that in a minute. So the basic idea is to have, instead of having one logic cluster, we have a group of logic clusters and internal routing channels. They are all powered by the same sleep transistor. And the idea here is the same as the single logic cluster. These signals that feed this multiplexer could come from any of the bordering routing channels to this region. So basically, we have a better chance now here to use one of these input pins to work as the control signal for the power state of the region. So as I said, there's a trade-off between area and the CAD difficulty because if we use larger regions, this means that the CAD tools have to work harder to group more logic clusters in the same region so that it can power gate them using one control signal. So we did evaluation for this architecture. The good is the potential leakage power saving in sleep mode. And the bad is the area overhead, the delay overhead because of the sleep transistors that exist in our architecture. And there's a leakage power overhead during the on state. So this shows our experimental setup. So what we did basically, we swept some architecture parameters, such as cluster size, channel width, and the size for the regions in our architecture. And we used 45 nanometer technology. We assumed the three architectures. Ungated architecture is the architecture with no power gating. It doesn't support power gating at all. Static gating is the architecture that supports power gating only at configuration time. There is no power control at runtime. And dynamic gating is our architecture, which supports dynamically turning things on and off at runtime. And this flowchart shows how we did these experiments. So the basic idea here is that we create sparse net list for our power gating architecture using some automatic tools, and we size the sleep transistors to make sure that the performance degradation is no more than 10%. So this is the basic idea what this flowchart is showing here. So we created these sparse net lists and did H-spice simulations to measure the leakage power for them.
Just a question?
Yep.
What did you mean in the top box there, automatic LC buffer sizing?
So basically, because we are varying the architecture parameters, like the cluster size and the channel width, we did some buffer sizing using the scripts. Like it was something, for example, if we increase the cluster size by X, we increase the buffering. Like we may add additional stage in the buffers of the input pins.
As an analytic function of those parameters, or as?
It's not analytical function, like in the sense that it is a function. I did experiments to get this right. Like it was by experimentation. Then I decided that like I can add them. If the size becomes so and so, then the buffer should be sized like this. Yeah. Okay. So here I'm showing leakage power savings for different region sizes of the architecture. So the x-axis here shows the region size, which represents the size, the granularity of our architecture. And the y-axis shows the leakage power for the region. What we can see here is that using power gating, these two overlapping lines basically, we get significant power reduction compared to ungated architecture. And as we increase the region size, the amount of leakage reduction increases. So basically the amount here is about 44% for region size 4. And it increases as we increase the region size. Of course, this number is 44% because we also account for switchboxes leakage, which we don't put in sleep mode. If we don't account for that number, if we assume only power gating for logic blocks, this number is larger than 80% to 90%. So I'm going just to zoom in part of this line to show you that there's overhead of dynamic gating compared to static gating.
Just a question before you go there. You're saying that the leakage is increasing as you raise R, is that right?
Yeah, it is increasing, but the leakage savings are
getting
increasing.
more. Oh, I
Yeah.
see.
Yeah. Yeah.
Where is static gating leakage?
Oh, it's these two overlapping lines. Like they are overlapping because like the amount, the difference is very small. Like they look overlapping because of the scale of the figure.
Why is the ungated leakage changing as a function of the region size?
Because it's function of the region size, right?
Is it divided by R?
Sorry?
Is this a square?
Yeah,
Like
it's
four is
a
4
square
by 4,
region.
so that's
Yeah,
why there's
square
a-
region. Yeah, it's square
Oh,
region.
so you're measuring leakage in a region of
Yeah,
size
for the
R.
region, yeah, for the whole
Oh,
region.
okay, you're
yeah.
not talking about an FPGA whose regions are of size R. You're talking
Oh.
about the leakage in a region of size R. That,
Yeah,
now I get it.
if we talk about the ungated, for the gating architecture, it should be in regions, right?
Just,
Okay.
at first when I see this as an architecture parameter, I assume R is a parameter of the FPGA.
Oh,
and,
it's,
and here you're saying, no, I am measuring a region
oh, okay,
of size R.
okay, I see what you mean.
So that's where I went.
Okay.
So,
Okay, does that make
but
sense?
no, I mean, it's the only way that red line makes any sense.
Okay, okay. So this is a zoom in of the two lines here, like if we assume that we change the cluster size. So we can see that the dynamic gating has slightly more leakage than the static gating architecture because of the additional circuit components, because of the muxes and the buffers that we needed. In the dynamic gating architecture, we have some additional overhead in the leakage. But the ability to turn things on and off at runtime is only available in the dynamic gating architecture, not the static gating architecture. So this overhead is about 11% compared to the static gating architecture. Also, we studied the amount of area overhead as we vary the region size. So these lines are the static gating architecture represented by the red line, and the dynamic gating architecture is represented by the green line. And they are compared to an architecture that doesn't have power gating. So we can see that the area overhead is decreasing as we increase the region size, because more resources are sharing the same sleep transistor, and we were able to get rid of some of the multiplexers that we needed for one track. The overhead here between the dynamic and static gating architecture is very small, in this figure. So the delay overhead that results from inserting sleep transistors is 10% by design, which means that we sized sleep transistors to make sure that the delay overhead is no more than 10%. Of course, there's a trade-off between the delay overhead and the area overhead. We can increase the size of sleep transistors at the cost of we can increase the size of sleep transistors to get less delay overhead at the cost of increasing the area overhead. So I talked about one of the issues, which is the architecture that we designed. And now I'm going to talk about one of the complications related to this architecture, which is the wake-up current or the inrush current. First, I will start by explaining what is the inrush current problem. So here I'm showing in this figure to the left a power-gated functional block and the sleep signal here is in the off state. So basically the PMOS transistor will be in the off state. So during that time, the internal nodes inside this power gated block will be discharging. The capacitance will be discharging. So when we turn this sleep transistor on, what happens is that a large current is drawn from the power supplies to charge the internal capacitance in the power gated block. And this large current here is called the inrush current. And because there are resistance in the power lines of the FPGA, basically this will cause an IR drop on the power lines of the FPGA, and this is called a voltage drop. So the problem with this voltage drop is that it will affect the performance of this is the first thing. Because if we have less voltage, the performance will be less, and it may cause violating timing constraints in the design. Also, the state for memory elements such as configuration bits or memory storage will be affected and may become corrupt. So this is basically what are the problems associated with inrush current. So if you remember from the beginning of the talk, I said that ASIC designers use power gating in their FPGAs regularly. So how they handle this problem of inrush current? So they use common two solutions here. So the first solution is that they turn on the power switches incrementally using some control circuit on the chip by controlling the value of the gate to source voltage of sleep transistors. A more common used solution is instead of using one large sleep transistor for a power gated circuit, they basically split the sleep transistor into smaller sleep transistors, as shown here in this figure. And the turn on of each stage is delayed by some amount. So because this sleep transistor is small, the amount of current that's drawn from the power supply at turn on phase, it will be small and it will not violate inrush current requirements. And the turn on of the next stage will result in a small current because there's some partially charged capacitance here. So this is the idea of daisy chaining the turn on. So how the problem is different in our FPGA architecture? So in ASICs, power gating is well known. The design is known by the designers. They know the inrush current requirements. In FPGAs, however, we don't know anything about the application when we design the architecture for the FPGA. The locations and sizes of power gated applications is not known when we design the FPGA architecture. And therefore, inrush current requirements are not known for the FPGA architects. So we need a solution that's configurable at configuration time to handle different application scenarios. Also, we studied the seriousness of this problem for our FPGA architecture, whether this is really a problem or not. So to do this, we created a model of the FPGA power grid and architecture. So the model includes multiple metal layers that represent the power grid of the FPGA. And the FPGA, as shown here, each cell of the FPGA was modeled as a grid of current sources. And these current sources are connected to the lowest metal layers. The values for these current sources were obtained using power analysis for MC&C benchmarks to get feeling how the power grid for the FPGA would look like, because we used them to design the typical power grid of the FPGA. And we studied the like if we replace those current sources I showed in the previous slides, if we replace them by the amount of inrush current for the power gating architecture. So what is the voltage drop will be? So this figure here shows the voltage drop for different region sizes. The x-axis shows the region size of the power gating architecture, and the y-axis shows the voltage drop on the power supply lines. What we can see here basically is that the voltage drop is more than 100 millivolt, which if you think about if we use technology where the voltage is less than 1 volt, this amount is a large amount. And usually they use 50 millivolt as a constraint on the voltage drop. So this is a large amount, and it means there is a danger of using this architecture without handling inrush current properly. So what are the possible solutions for our FPGA architecture? We can just ask the designer to take care of that. So how is that? So the designer, when designing the power control circuit, he or she might design it so that it wakes up one power getting region in a power domain at a time, using multiple control signals that come from the power controller. However, this requires the designer to have experience and knowledge about the FPGA architecture and inrush current requirements. Also, it complicates the design process, which is not desirable for FPGAs. Also, it may result in a power controller with large power consumption that may offset the benefits from this kind of architecture. So what is our solution to this? We propose an architecture which allows limiting inrush current in a configurable way. So the solution has two levels. The first is fixed intra-region level that ensures that individual region in the architecture is turned on without violating inrush current and voltage drop constraints. And the higher level is a configurable inter-region level that safely sequences the turn on of multiple regions in one power domain. First, I will start talking about the fixed intra-region level of the architecture. So in this figure here, I'm showing a power getting region. I'm hiding the details inside this region. And these are the signals that come from the bordering routing channels. And this multiplexer is used to select one of these to work as the control signal. And the change here is that instead of having one large sleep transistor, we break this sleep transistor into smaller sleep transistors so that when we wake up this region, a small current will be drawn from the power supply that is less than the constraint. So this makes sure that we can turn on this region safely. The values for these sleep transistors and the values for the delays used here are determined when we design the architecture for the FPGA. And they are based on how much current the power grid can provide without violating the inrush current requirements. And there's a trade-off between the sizing for the power grid and the amount of delay elements here. Because if we increase the size, we will get larger current from the power grid without violating the constraints, so that we can use less number of stages and therefore less number of delay elements. So the area overhead becomes smaller. So we did experiments to investigate this level of the architecture, and we used these settings here. The region size we assumed 4x4. Power grid was assumed to be typical one, not oversized. We used the worst case temperature, and we evaluated two things. So in terms of leakage overhead, we evaluated how much leakage savings we could achieve with the existence of these additional delay elements in the architecture. So the savings could be up to 94%, even with the existence of these delay elements. And without the existence of these delay elements, it was 97%. So the overhead, as you can see here, is small. Also, we studied the area overhead compared to ungated architecture, and the additional delay elements caused area overhead of less than 1%. Now I'm going to talk the configurable inter-region architecture to handle inrush current. So theoretically, intra-region architecture that I talked about in the last few slides could solve the problem because it allows turning on one region safely without violating the constraints. However, in practice, what might happen is that more current can be drawn during the turn-on of regions due to switching of unrelated signals that are routed between the different power domains, also because of switching of inputs to logic clusters during the turn-on of the power domain. And these are application dependent. So instead of turning a complete bar domain or bar-gated application at once, what we can do is that we can turn on one bar-gated region at a time, or maybe more than one bar-gated region at a time. But I will explain how to turn on one bar-gated region at a time. So the idea, to explain how this works. So if this is a bar-gating FPGA with bar-gated regions, and this represents an application that's mapped to 4 of these regions. So basically we want to insert some delays between the turn on of regions. So here we turn on one region, after some amount of delay we turn on the second region, and so on. So we need to insert delays between the turn on of different regions. And basically we don't know at the architecture design time, we don't know how these will look for the different applications. And we don't know how many delays are required for the turn on of each region. So we need a configurable solution, and a configurable solution that can provide us with different amounts of delays as needed for different applications. So to achieve this, we use a programmable delay limit, and I will show you how. So this is the bar-gating region I showed you before. And everything is the same as I showed you before, except the addition of this programmable delay element here. So basically this programmable delay element, if configured properly, could delay the wake up of the region as a whole. And let's zoom in the programmable delay element. So basically it is a multiplexer that has its inputs coming from delay elements. So the selection lines for these multiplexers are controlled using configuration bits, and it could determine how much delay is produced by this programmable delay element. And this is done at configuration time when we know about the application and we know how much each region needs delay before it is turned on. One thing here is that the size of this multiplexer, or how many delays can be generated by this programmable delay element, is related to the largest power-gated application that can be power-gated by the same signal. And I will show you an example what I mean by this. So here I'm showing an FPGA with power-gating regions of our architecture. And I represent each region using this, only the delay element, using the programmable delay element. So if this is an application that's mapped to 4 of these regions, and we have a programmable delay element of size 4 here, it can provide 4 delays. So these programmable delay elements could be programmed so that it sequences the turn on of these regions in a proper way to limit inrush current to our constraint. As you can see here, the one in the corner is programmed with 1 delay element, the one next to it is 2 delay elements, and so on. So this is in the case that the programmable delay element has 4 delays and the application has 4 regions.
Just a question.
Yep.
I think you have an assumption that there's another control signal that activates the circuit itself. Is that correct? That while it's powering up, it can't actually be wanting to change its state, for example. Is that right?
Yeah. So, I mean, when the architecture is perfect, what we assume is that there should be a handshaking signal that tells that, the power-gated domain is turned on, right?
The circuit itself knows that it can begin computing.
Yeah. Yeah, there should be. Yeah, I think this is our assumption for now. We are basically focusing on the architecture because that could be done in in the application when the application is designed, right?
That signal and
yeah.
Something else will control that signal. Is that right? But where I'm going, what I'm wondering is there, even if the existence of such a signal that's in that controls that region that says, do not, what would be a clock gating thing, perhaps? Something that stops the clock from ticking, right?
Yeah, probably.
What if its outputs are talking to something else that is active?
Okay, so the outputs, I didn't show that in the details of the architecture, but the outputs will be pulled up or pulled down until the whole region is turned on. And there should be something, some handshaking signals from the controller itself that tells the other component,
Not to listen.
yeah, not to listen until this whole thing is turned on.
Okay, so there's
Right.
some,
Yeah, just for clarification, are you assuming that these regions are coming up from a fully powered down state, or are you talking about sleep in the sense that there is some state still held by that region that you want to preserve?
Yeah, so one assumption in our architecture is that we don't apply power gating for storage elements. So there's a state, like there's internal state that's stored in these power blocks. So we power gate buffers, like circuit components that can be power gated, but for memory elements we don't power gate these to retain the state of the logic blocks. Does that make sense?
That includes flip-flops inside
Yeah,
the
yeah.
logic blocks?
Yeah, yeah.
Okay.
Okay. So this is like if the application size is similar to the size of the programmable delay element. So what if the application size is smaller? It's straightforward. We can just use two delays to delay the sequence of this, to sequence the wake up of the application. What if the application size is larger than what the programmable delay element could provide? So basically we leave that to the designer. So basically, okay. So basically here we have four regions that are controlled using one control signal, which is C1, and the extra two regions in this application are controlled using another signal, which is C2, that's delayed from the power controller that generates these signals. So the power controller should provide the power delay to sequence the wake up of these two regions after the wake up of these four regions. So we did some experiments and used these settings: region size 4x4, typical power grid. We assumed worst case temperature. We assumed that the programmable delay element size is 50 in our experiments. So we found that the leakage bar overhead, because of introducing these programmable delay elements, is small. This shows 94% leakage savings of the power gating architecture with the programmable delay elements, and without them we have 97% leakage power savings. So the overhead is small. The area overhead is also small. It is less than 2%. So we did some system level evaluation for the whole architecture after we get all of these results. And we used a model, for example, to find what is the upper bound on the savings that could be achieved from this architecture. And this model basically relates the application behavior and the application structure to the amount of savings that could be obtained from this architecture. So here I'm showing, like, on the x-axis and y-axis, basically they show the application structure. What is the fraction of regions that in that application that could go into idle mode during the execution time of that application? And in this axis, I'm showing the application behavior. So what's the percentage of times these regions could go into sleep mode? And the z-axis shows the leakage reduction. And I'm showing here two architectures: the static gating, which allows only power gating at configuration time, and the dynamic gating, which allows power gating at runtime if the clocks are idle. And they are compared, the leakage savings here are compared to an architecture that has no power gating. So if you look at the values where we have small fractions of idle regions and small fractions of idle times, we can see that the static gating has larger savings than dynamic gating. This is because dynamic gating basically is equivalent to static gating in the sense that you can just turn off things that are unused, because everything will be used all the time. And because dynamic gating has some extra circuit components, it has more leakage power overhead, so the static gating achieves more leakage reduction. However, for the majority of this service, you can see that the dynamic gating architecture could achieve more energy savings that are consistent compared to static gating, because it can turn things that are idle when they are idle. However, static gating couldn't do that. So the leakage savings from static gating are reducing as the activity of the application and the amount of regions that could go into other region increases. I think I will stop here. How much time I have?
A few more minutes.
A few more minutes. Okay, I just want to explain this, and then maybe stop after that. Also, we evaluated conditions to achieve energy savings using the architecture. So the basic condition is that the energy that is consumed in sleep mode should be less than the energy if you left that application without putting it in sleep mode. And basically this energy that's consumed in sleep mode could come from two sources: the energy required to enter and exit sleep mode, and the energy during the sleep mode itself, because there is still some energy that's consumed, although it is very small. And we created a model that relates the architecture parameters, these energies and the application, to the minimum idle time required to achieve energy savings when in sleep mode. And we got this line. So basically this shows, as a function of the programmable delay element size, what is the minimum idle time to achieve energy saving for application, for example, for CLMA, which has 775 tiles. The minimum idle time was about 900 nanoseconds. So if the idle time for that application is more than 900 nanoseconds, then it is feasible to put that in sleep mode when it is idle. Otherwise, it is not feasible. And this is equivalent to about 500 cycles when we talk about 500 megahertz. So our current work basically focuses on propagating the switch blocks. There are some other issues related to the architecture, such as mapping of applications to this architecture, how we can automatically detect power domains in applications, and how we can automatically create power controllers. Also benchmarks. We need benchmarks for this architecture. We don't have real benchmarks that basically have power domains, multiple power domains that go on and off at one time. So in summary, I talked about our power gating architecture that supports dynamically turning things on and off at one time. I showed you how the architecture looks like. Control could come from on-chip or off-chip and routed on the FPGA routing resources. I also presented a way to handle inrush current in a programmable way. There are some challenges such as the area overhead, the performance degradation, which can be traded off for area. And another important challenge is mapping of applications to this architecture. Thank you.
Do we have any questions?
Yes.
So, from what I understand, you said that the dynamic gating and static gating were very similar. But for static gating, you're turning off sections of the FPGA you're not using, so you can actually gate out the SRAM bits and storage elements as well, right? So shouldn't that decrease static power significantly?
Well, if you assume that these components have large static power, right? But what usually done in FPGAs is that they use thick oxide, they increase the length of transistors so that the leakage power of these components is very small. So why we just assume that we don't get these components, because we assume that they consume a low static power. But you are right, if they consume a lot of static power, that makes sense to propagate these components as well.
What do you assume about switching activities when you're sizing your power switches?
Excuse me?
What do you assume about activities, so switching activity when you're sizing your power switch?
Active leakage?
No, like when you said you're resizing your power switch for regions of various sizes.
Mm-hmm.
So those regions will all have different dynamic power requirements.
Yeah.
Which is
So basically the power switch size will increase, right? So we did iterative sizing for the power switches in order to get 10% performance degradation.
Or are you assuming like if you double region size,
So it will be less than double. Because some of the resources are shared, like they are sharing the same capacitors, like because of the statistical behavior of the things inside the region. So basically, if you double the region size, this doesn't mean that you will double the size of the sleep transistor. It will be less than the double. And this is why the area overhead decreases as we increase the region size. Does that make sense?
Yeah, I guess I'm just wondering specifically how you model it. I mean, do you have, say, typical inputs?
So basically, yeah, so basically I assumed the worst case inputs. Like I assumed all the inputs to the region coming on the region to be, for example, all of them on or off. So that like to find what's the worst case size for the sleep transistor. Okay.
Any other questions?
Yeah, I had one. Need to work it through. There's a trade-off between performance and leakage power consumption, right? Just forget prior to your work. That if you give up, if you want to give up less leakage, you can do it by asking for less
Voltage.
Voltage
Yeah.
or threshold voltage. There's
Yeah.
a fundamental trade-off
That's right,
there.
yeah.
And so I'm just wondering if you'll, where you were saying we will give up in order to do this 10% performance, that's a different, you're using a different method to trade, or you are trading leakage for performance. And so I wondered if perhaps you should compare to those alternatives as opposed to the base case.
Yeah.
Does that make sense? It's just sort of.
Yeah, I think it makes sense. But like, I think our solution is orthogonal also to this, right? Because even if you trade off some performance, you could also turn things off at one time.
It's not 100% orthogonal.
Yeah,
I think
not
it
100%
is
orthogonal.
disconnected,
Yeah.
partially disconnected,
Yeah.
not 100%
Yeah.
orthogonal.
Yeah.
And that's making me think that the comparison, a slightly more fair comparison would be against those alternatives, just to give some sense, particularly if those were programmable, right? Like the all-pair programmable power lets you do that dynamic trade-off too, right? Power and performance and leakage power, right? When you pick the two threshold voltages with different body bias or something, right? That's what these folks do. So it is also dynamically tradable, and it's just a thought that might make an interesting and important comparison.
I wonder if you have an idea about whether to kind of get substantial savings out of this, the designer needs to design it with kind of power savings in mind, design like their applications so that you have kind of disconnected large regions, or whether kind of you can apply this to some basically like as with current design methods and get savings.
Yeah, I think, what you are saying completely makes sense. Because the designers should have this in mind when they design their applications. Similar to what ASIC designers have, right? Yeah, and this should be fit to the design flow in some format to tell the tools that these regions are, for example, this is power domain 1, this is power domain 2, and this is the power controller, and these are the control signals that control the power domains. So yeah, it makes sense, but my focus in this work was on the architecture itself that supports all of this.
Related question,
Yep.
what happens to signals that don't belong to a power region, that are just passing through from between two unrelated regions? You don't currently power gate your switch boxes, so they're not affected, but don't the signals go through routing channels as well between switch boxes? So what happens to those signals which are just passing through? Wouldn't they get turned off necessarily?
Okay, so in routing channels, I mean the track isolation buffers and the connection blocks. So basically, you don't have these repeaters like the buffers to repeat the signal in the lines or the tracks in the routing channel.
Okay, so
they will not be affected.
Okay.
Yeah. Like we assume that these repeaters are in the switch boxes.
Then follow up. If you could force the CAD tool to route around, then you could turn all of those off, because then you guarantee that the routing, that those wires themselves, the routing belongs only to signals that come from within a region to the same region.
Yeah, that's possible. Yeah, but you know, this needs investigation because this might have some performance overhead. Yeah, this is interesting, I think.
So sleep transistors do leak. So if we assume the 10% performance degradation, what is the theoretical maximum power savings you can have if you say was able to sleep the entire FPGA?
So if we are able to like turn on the whole FPGA, we can achieve 44%. The 44% I showed you in that graph. So this is the upper bound. Of course, that 44% includes the leakage for switch box, which we don't forget for now. So for logic clusters, it is more than 80%. Yep.
For the 44%, did you include the rush current in, or?
No, for that part, we didn't include the rush count. So that part was done before doing the rush count part. But in the presentation, I just rearranged them to make it looks make sense.
Essentially, it's around 30% most likely. It will be enough.
Well, like for rush count, the overhead is about 3 to 4%. So maybe 40%, little bit less than 40%. Yeah.
Okay, thank you to the speaker again. Okay, so we're waiting for alternative